So let's do, let's see. This says it's chapter 6, but in your book, it's chapter 5. So in Brown, we're looking at chapter 5, thermochemistry. A marker out. There we go. All right, so let's review. Number 2. What's the kinetic energy of a 1.56 kilogram object moving at 94 kilometers per hour? And so we know that the mass is 1.56 kilograms, correct? Mm-hmm. Okay. And its velocity is 94 kilometers per hour, correct? Okay. And what formula are we going to use to determine the kinetic energy? Remember? Mass times velocity squared. Okay. Now, yeah. Okay. Okay. The unit in the SI system for energy is the joule. But if you want joules as your answer, these have to be SI units also. Right. So we're good with this one because kilogram is the SI unit for mass. But kilometers per hour is not the SI unit for velocity. Velocity is, right, meters per second. And then we have to square it. So we got to convert this to meters per second. Okay. That's the trick to this one. Kilometers per hour. So remember, when we have 2 units that have to be changed, we do them one at a time. So let's do kilometers first. We got to get rid of kilometers. So it's in the denominator. So it'll cancel. And then we want meters in the numerator. So what's the relationship here? 1 kilometer is 1,000 meters, correct? Okay, that takes care of the meters. Now we need to get rid of the hours. This is in the denominator, so that one's got to be in the numerator. Do you know how many seconds are in an hour?
1,000.
All right, let's go like this. Let's do minutes per
60 times 60. 30. So to do 1,200.
3,600, right?
What the freak am I talking about? I don't know. It seems confusing.
There you go.
I'm thinking of something in a mile.
5,280 feet, 1,760 yards.
Yeah.
Okay. Okay, so now we got rid of hours and we got meters per second. That was the thinking part. Now we just need to crunch some numbers. So 94 times 1,000.
What's on the top? Meters?
Yeah, meters per kilometer. 10 to the third.
I didn't
And divide by 3,600.
10 to the third divided by 36.
No, 10 to the third times 94.
1,000 times that.
Right. It might be easier to do it this way. I know some of my students like to do it this way. They just say like that. They put 94 kilometers here, hours here. They put 1,000 meters here, kilometers here. 1 hour here.
That's how they do that.
3,600 seconds there. If that keeps you straight from making a mistake, do it that way. I don't care. I use parentheses.
Well, that way at least you can say what you did wrong.
Yeah, and a lot of my students make the mistake of putting the numbers into their calculator wrong. Instead of something divided by something, they say, or A divided by B, they put it in their calculator, B divided by A. And that will never do. So I get 26.1. Let's see, 3 significant figures. meters per second. And remember, this is a conversion factor. That's a conversion factor. Those are exact numbers. The only one that determines the significant figures here is this one.
26.4.
So now we've got kinetic energy equals 1/2 times 1.56 kilograms times 26.1 meters per second squared. Okay. I've already got this in here, so I'm just going to square it. And then times 1.56 and divided by 2. So I get, let's see, 3 significant figures. Rounded off, I get 532. 32 joules. Oh, look at the answer. It's in kilojoules. Yeah, K. Kilojoules, 1,000 joules. Don't you remember prefixes?
Yeah, I didn't know.
Okay, so if we want to convert this to kilojoules, right? Joules here, kilojoules here, it's 1,000 joules per every kilojoule, right? Because this right here is the same as that right there. So if we divide this, we get 532 times 10 to the minus 3 kilojoules, because we cancel joules. And then, but 532 is 5.32 times 10 squared, right? We move the decimal 1, 2. There it is right there. But it's still times 10 to the minus 3 kilojoules. How do you combine this one with that? It's the same base. Add them together. Right. 5.32 times 10 to the minus 1 kilojoules. There you go. Now, that one's A. That's the long way. If you get comfortable with these unit changes, then you can probably do that in your head eventually. Yeah, A's the end. It's right there on the document. I didn't write it on the board. Yeah, it's picking it up. It's only chopping off just a little bit up here. Okay, number 3.
That box somewhere.
Huh?
I'll move that box somewhere else.
Oh, yeah, sure. Just set it on the bench over there. All right, number 3. Which of the following statements correctly describes the sign of Q and W for the following exothermic process? All right, so we've got the process is water vapor going to water liquid, right? It's condensing from a gas to a liquid. And it's an exothermic process. It tells you right there. Is that reasonable? Should it lose heat going from gas to liquid? Yeah, definitely exothermic. So delta H, the enthalpy, change in enthalpy. Let's see, we didn't do this during lecture. Right, you see it, you saw it in the video. Okay. This is going to be a negative value. Actually, they tell us what it is, don't they? No, they don't. They tell us what the pressure is. Pressure equals 1 atmosphere. And at 370 K. temperature. Okay, that's everything that's given to us. Now they want to know what Q and W are. All right. Q and W. What does Q stand for? Heat. Q is our variable for heat.
Man, I was wrong.
And in order for heat to be measured, you need to
What's that be?
work.
Oh, I didn't
This
know
is
that.
heat, and this is work.
I didn't know that.
Remember, internal energy is determined by heat and work, the internal energy of your system. So if we have a system down here, if heat is being added to the system, it's going to be positive. Everything is relative to the system. So a transfer of heat into the system is positive, out of the system is negative. So if the system does work on its surroundings, like this, that's going to be a negative. System is doing work on its surroundings. Okay. All right. So this is one where it would be good to have a picture. So if we have this cylinder, and it starts off with water vapor. Okay. And the pressure is constant at 1 atmosphere pressure. Then when this goes to liquid, what's going to happen to that piston? Right. The gas is not going to occupy the same amount. I mean, the liquid's not going to occupy less volume. So as it goes to liquid, right, it's going to be down here like this instead of gas up here. So the piston's going to drop. When this piston drops, the system is having work done. Let's see. Yeah, it's doing work on the system. So it's going the other direction. W is positive. Surroundings are doing work on the system. Right? Because the work is force times distance. We got a force here, and it's moving this distance. So the work is being done on the system. That takes care of this one. How about heat? Well, it says exothermic, right? So that means, right, heat is leaving. So this one's negative. And also, I don't know if you caught this in the video, but Q and delta H are not necessarily the same thing. Delta H is an enthalpy. It's a state function, and it's a potential for energy production or energy absorption. The key is pressure. If pressure is constant, then they're both the same. Okay. I hope that was in the video.
Yeah.
If pressure is constant, then delta H equals Q. And that's why chemists.
Because it stays constant.
Well, because this is constant, yeah. But there's a whole derivation that I went through in the video about why that's true. Yeah. And that's why chemists try to conduct experiments thermochemistry experiments where pressure is constant, because you can measure this. This is not measurable unless it's related to that. It is measurable, but it's very difficult to measure this. It's easier to measure that because all you need is mass, change in temperature, right? Remember the Q equals S mass delta T. We'll talk about that some more because that's part of the lab. Okay, so our answer then is Q is negative, W is positive. Q is negative, W is positive. C is the answer for this. Before we get to the next one, we had E equals Q plus W. Any change in internal energy, change in enthalpy is equal to change in internal energy plus a change in pressure times volume. Okay, so what we did was we derived it in such a way that if the pressure is constant, then we bring the P out here and only the volume changes. And then we filled in values, like we filled in these values here, Q plus W plus P delta V equals delta H. And then W equals a negative P delta V. Remember that one? So when you put that one in here, negative P delta V, then these two cancel. So when pressure is constant, that one equals that one. Okay, if that sparks a memory. Okay, let's move on before I waste the whole day. Number 7. 1 mole of an ideal gas is expanded from a volume of 1 liter to 8.93 liters against a constant pressure. How much work in joules is performed on the surroundings? Okay, we're going to ignore significant figures. Right, I like to draw pictures. So we got a piston here, right? And the volume inside here is 1 liter. And then it's going to expand to here. And the volume inside here is 8.93 liters. That's not to scale. Under a constant pressure of 1 atmosphere. All right. So the amount of work done is that formula I gave you earlier. Negative P delta V. What? Okay. So we can calculate the work is negative pressure, 1 atmosphere. And delta V is always final minus initial. Any delta is always final minus initial. So final is 8.93 minus 1.00 liters. So that's 7.93 times 1. It's negative 7.93 liter atmospheres. Our answer is in joules. So we got to convert this to joules. Okay, so far? Okay. So we need a conversion factor, numerator, denominator. All right, so what's the relationship? It's given to us there. One liter atmosphere is 101.3 joules. 101.3 joules. 1 liter atmosphere. So multiply those together. And in joules, that's 803. Minus 803 joules. So that's how much work was being done by the system on its surroundings. If it goes from here to here, it's pushing against its surroundings. That's the way I look at it. And that tells me it's doing work on its surroundings as the gas expands. It's like, think of a piston in your engine. Right? When the piston fires and the gas and the air explode, the piston moves down. And as the gas expands, it's doing work on the crankshaft, which goes all the way down to your wheels and turns, and there you go. Doing work on the surroundings. That was 7. Huh?
We're talking about some of, like, we've heard the word pistons, we couldn't figure out why.
That's the guy said that.
Oh, you don't know how, you don't know an.
No, I do. It's from a game.
Oh, okay. Okay. All right, that's 712. Calculate the work associated with the compression of a gas from 121 liters to 80 liters at a constant pressure. Okay, This is a similar type of problem. Minus P delta V. In this case, it's even simpler because you don't have to convert liter atmospheres to joules. But you do need to know what to put in. See, negative. Pressure is constant at 13.1 atmospheres. Okay, what's delta V? What's the final? The final is 80 liters, isn't it? Compression from 121 to 80. Okay, so 80 is the final minus 121. Okay, so this is going to be a negative. That's a negative. Our answer is going to be positive. Right? Work is being done on the system. And if we do our calculations right, it should be 537. Notice there's an answer in there with a negative on it. That's so if you do the wrong subtraction here, you get the wrong answer there. Okay. It's sneaky. Testing to see if you know final minus initial. That was B, I think. All right. Well, all right. 14 through 17 is based upon this top statement, and then I'll scroll down. 14, 15, 16, and 17. Based upon these facts, a gas in a 1 liter bulb, so this is 1.0 liters, got a gas in there, at standard temperature and pressure. So what's standard temperature and pressure for a gas? Standard temperature is 0 degrees. 273 K. And pressure? Yeah, Kelvin. Pressure is 1 atmosphere. Okay, those are the conditions. Oh, this bulb is connected to another bulb with a valve. It doesn't tell us how big this bulb is, but this one's a vacuum. Okay. All right, now we need to say something about Q, W, which comes next? Internal energy and enthalpy. Internal energy change, enthalpy change. All right. All right. The question is, when we open that valve, we know what's going to happen. Right? The gas is going to rush into the vacuum. Right? But we need to say something about heat change, work done, internal energy, and enthalpy. So we can take our pick. Which one comes first? Well, if it's at constant temperature, then there's no change. You don't get heat movement unless there's a difference in temperature. So when that gas expands into here, as long as the temperature is constant, this one's equal to 0. There's no heat movement at all. And work was work done. It wasn't pushing against anything. It was just expanding into that space. So there's no work done either. Well, what's delta E? It's Q plus W. That's 0 also. Now, delta H can be written this way, plus V delta V. Let's see. This is the one that always gives me trouble. If pressure were constant, then this one would be equal to that one, and it would be 0. But there is a change in volume, and inside this container, there's a change of gas. But they're inversely proportional. So however much this one changes, that one changes by the same amount. So they cancel each other out, is the way I look at it. Did my review document explanation, did it offer something better? Number, I didn't even write the number up there.
Mhm.
No, I did, right here, 14, 15, 16, 17. So let's look,
We don't have anything.
they're not in there? Oh, okay.
And so. Yeah, yesterday.
So, yeah, I guess I just figured that. Is there any energy change at all in this process? Answer, no. No energy change whatsoever. So delta H, the enthalpy should be 0 because it's a state function. These two are state functions. They only care what started, what ended. And if they start and end with the same value, then we don't care. It's 0. 0, 0. All of them are 0. Okay, that was up through 16. Let's scroll down. 18. All right, I told you this one. 18. How many of these are state functions? Energy, work, enthalpy, or heat? Well, I got them highlighted there. Energy and enthalpy are state functions. In other words, we don't care how they got from one place to another. All we need to know is the beginning and the ending. Whereas work and heat are path functions. It does matter what path they take to get where they're going. I'm sorry. The analogy I use is going from Beckley to Charleston, or from Charleston to Beckley. It used to be the road. I mean, before the turnpike was in there, you had to go right windy, windy, windy up the mountain. And so the amount of work required to get there is a lot, and a lot of heat expended to get there in your engine is a lot. But now you can go from Charleston to Beckley, an elevation change of about 2,000 feet on a straighter path. Right? It takes less work. But if you want to calculate how much energy did I gain in the process from going from that level to this level, all I need to know is what's my position here, what's my position there, the difference in height times the acceleration of gravity will give me the amount of energy, the potential energy that I've stored as a condition of change in height. So that's the way I look at it. Oh, so the answer is 2, C. How about 19? By the way, this is thermal chemistry is kind of an introduction to thermodynamics. So we don't get into thermodynamics until next semester. And then we talk about the reason why that gas moved from this bulb to that bulb. It's a little thing called entropy. We'll talk about that in more detail later, if you decide to come back. Which of the following properties are intensive properties? All right. An intensive property, remember, is a property that can change, that cannot change with the amount of stuff. Right? The amount of mass or volume or whatever the case may be. It's immune from that. In other words, if you have density is a good example. If you have a 24 karat gold ring, it's got a certain density. If you got a 24 karat bar of gold, then it's the same density, right? Because it's a proportion. Mass per unit volume. So if you increase the volume, you increase the mass proportionally. So you get the same density. All right, so mass is an extensive property, not intensive. Temperature is an intensive property because it doesn't matter how much of the substance you have. If it's at a certain temperature, you can have a little bit or a whole lot, and it'll be the same temperature. So that one is intensive. Volume, no, increase the volume, right? The value changes with more stuff. Concentration, right? If you have so many moles per liter, that gives you molarity, then the amount of the solution, sorry,
No.
didn't we haven't covered molarity yet?
Yeah.
Okay. If you have more volume, then you're going to have more moles. So the ratio is always the same value. Right? So concentration is an intensive property. Energy is an extensive property. Because if you have more heat transferred, you have more energy change. All right, so, and temperature is kind of strange because it's a single value that is an intensive property. Right? It's a measure of the average kinetic energy of all particles in your stuff. But most of the other intensive properties are ratios, something to something. Oh, so the answer is Roman numeral 2 and 4C. Those are the only intensive properties in that list. About 23. All right. For this reaction, C2H5OH is what? You may not recognize that. It's ethanol. You know, the drinking kind. Only in this case, we're going to burn it. We're going to combine it with oxygen and make carbon dioxide and water. And there's the enthalpy value associated with it. You can tell from the delta H that it's exothermic because the value is negative. That's the first clue. So consider the following propositions. Number one, the reaction is endothermic. No, we just said it was exothermic. All right, so Roman numeral 2 is correct. It's exothermic. How about 3? The enthalpy term would be different if water formed was gaseous. Right, notice that this formula has, or this reaction has water as liquid as one of the products. What if it were a gas? Would that change the enthalpy value? Yeah. Because if it were a gas, it hadn't condensed yet. It's still got the energy, right? So the delta H would be a smaller value. Maybe not much, but it would be smaller. Right? So the phase, for thermochemistry, the phase of your reactants and products matters to the value that's assigned to the enthalpy. So 2 and 3 are the correct answer, which would be E. Okay. All right, 24. How much heat is required to raise the temperature of 5.75 grams of iron with the specific heat from 25 to 79.8? All right. So what we're given is 5.75 grams. 5.75 grams is the mass of iron. Okay. The specific heat, which is S for iron, is 0.450 joules per gram degree C. That's the units of measure. And temperature, the initial temperature is 25 temperature, initial temperature is 25 degrees C. And the final temperature is 79.8. Okay, so I go back to our formula that I gave you earlier. This is the formula for calculating the heat that's required to raise the temperature of something, or the heat that's given off by something when it lowers its temperature. It's S mass delta T. So the specific heat, the mass of the substance, and the mass is determined by this value right here. This is a constant. So if this has grams in it, that needs to be grams. This has degrees C, this needs to be degrees C. And then our answer will come out in joules. Okay, so now we just need to put everything in its proper place. 0.450 joules per gram degree C times mass, 5.75 grams. And then delta T, final minus initial, 79.8 minus 25.0 degrees C. And that'll give us joules of heat. Right. And if you do your calculations right, you should come out with 142 joules. Okay. Scroll to the next one. You're deciphering my writing.
No, I'm just on this way.
Now that formula for Q is good as long as there's no phase change. If it stays the same phase, that works. If there's a phase change, then you have to introduce another formula for heat of fusion or heat of vaporization, one or the other. 26. Right? That's right. Yeah, 26. Guess we'll start to poop out on. See if I got another one that works. So far. Okay, a 32.5 gram piece of aluminum, which has a molar heat of blah, blah, is heated to 82.4 degrees and dropped into a calorimeter containing water. Specific heat there. Initially at 22.3 degrees. So the hot aluminum piece is dropped into the cool water. And obviously, some of the heat's going to transfer from the aluminum into the water. And when they come to equilibrium, they're going to be at the same temperature. And that temperature is 24.2 degrees. What's the mass of water in the calorimeter? Okay. First point is we're not considering the calorimeter's contribution to any heat changes. We're just assuming that it's perfectly isolated and the calorimeter is not contributing any heat or absorbing any heat. Okay. That never happens, but except in these hypothetical problems. So we only have to be considering change in temperature for the water, change in temperature for the metal, those two. So remember, I was going to say, since we didn't go through this in lecture, this is an isolated system. Remember what that is? No heat transfer between the surroundings and the system, and no mass transfer. Right? It's isolated. That's our styrofoam cups. That's our calorimeter that we're going to be using. And it's perfectly insulating in this case. It's isolated. That means that anything that happens in Vegas stays in Vegas. So all the heat calculations add up to 0. And we've got a heat change for the metal, aluminum, and we've got a heat change for the water. And those two added together has to be equal to 0 because the system is isolated. All right. So now we can expand these to take into account this Q for aluminum, which would be the S for aluminum times the mass of aluminum. Is that the way it's set up? Aluminum specific heat is given in terms of moles. So we're going to need moles here for aluminum. And then the change of temperature for aluminum. So let me put this up here. What's the mass of aluminum? 32.5 grams. So we've got to convert that to moles. Otherwise, we can't use that value that's given in the problem. All right. And then we add S for water. And this one is in terms of mass. So that one works okay. And temperature change for water. Think about these calorimeter calculations. You've got to be extremely methodical setting them up, because there are so many moving parts. If you don't, then you'll just pull your hair out trying to solve it.
Once they're set up, I'll file.
Okay, let's change this to moles. So 32.5 grams. And what's the molar mass of aluminum? I can't see it from here. There's a reflection. 26.98. 26.98 grams. Well, that'll tell us how many moles of aluminum we have, and then we can use the value that's given here for our specific heat. Sometimes specific heats are in terms of grams, and sometimes are in terms of moles. 32.5 and 26.98. So that's 1.205. 1.205 moles of aluminum. Okay, now we can break the problem out. 0 equals the value that was given was 24.03. 24.03 joules per mole degree C. And then moles of aluminum is 1.205. Oops. Close my parentheses too soon. Okay. And then change in temperature is final minus initial. So what's the final? 24.2. Right, 24.2. And what was the initial for aluminum? 82.4. Aluminum. We heated it up to 82.4. Okay, that was the initial. Okay. Then for water, S for water is 4.18 joules per gram degree C. How many grams of water? That's the question. Mass of the water, that's the unknown. That's what they're asking us. 22.3 was the initial for water, so it's 24.2 minus 22.3.
What's in that middle parentheses? The M?
Here,
Yeah.
that's the mass of water. That's the unknown. I mean, the question says, what's the mass of the water? And it's like any math equation. Now, we've got one unknown. We can solve it. All right. So this one has no unknowns in it. So we can do this whole calculation right here and come out with a single number. I want to do this first. 24.2 minus 82.4. So guess what? That's a negative number. It's 58.2 right here. Times 1.205 and times 24.03. So everything here in this area is minus 1685 joules. Right? Because degrees C canceled, moles canceled. We're left with joules. This one over here is going to be is going to have an unknown in it. So we need this value right here, 24.2 and 22.3 subtracted from that is 1.9. And 1.9 times this value is 7.952. 7.952 times the mass of the water. Okay. That's a plus. All right, so we have, let me bring everything down here. 0 equals minus 1685 joules plus 7.952 mass of the water. Okay. So if we bring this one across the equal sign and put it on that side, it makes it positive. 1685 equals 7.952 mass of the water. And the mass of the water then equals 1685 divided by 7.952. I get, let's see, how many significant figures do I have? 4? 21.19. No, 211.9 grams. Rounded off. Okay, they're only using 3 significant figures, so it's 212.
How did you make that? Oh, you transferred it on the other side.
Yeah. We lost the sign when we went over on the other side. Okay. All right, that took a while, but I wanted to do it in nauseating detail so you'd see every single step in the process. Yeah, I wrote it too low. Let's see, is the camera catching it? Yeah, it's on there. All right,
Equals 212.
212, yeah. Now it's 26. Oh, excuse me, 27. A 45.9 gram sample of metal is heated to 95.2 degrees Celsius, placed in a calorimeter containing 120 grams of water at 21.6 degrees. The final temperature of the water is 24.5. What metal was used? We're going to use the specific heat of the metal. We're going to calculate that part. Okay. We're going to calculate the specific heat so we can determine what, out of those that are given, which one is the correct metal. So, let's put everything over here. The mass of the metal is 45.9. Mass of the metal, 45.9 grams. The mass of the water is 120. Okay. The final temperature. The final temperature of the water is the same as the final temperature of the metal. Once they come to equilibrium, that same temperature. So that final temperature is equal to 24.5 degrees C. Now, the initial temperatures are different. The initial temperature of the metal is 95.2. And the initial temperature of the water is 21.6. Okay. I think that's everything that we're given except for, notice this is an old question because they're using little c for the specific heat of water. We're using S. It's the same thing. All right. So when we set it up like this, 0 equals the heat change of the metal plus the heat change of the water, and we're ignoring the calorimeter again. All right, so if we expand them, then we have specific heat of the metal, which is going to be our unknown. We don't know that. The mass of the metal times the change in temperature of the metal. And then for water, we do know that one. We do know the mass of the water, and we can calculate the change in temperature. All right. So we're going to have this as our unknown. And the mass of the metal is 45.9 degrees, grams. And then the change in temperature is final 24.5 minus initial 95.2. And then plus the water factors, which would be 4.18 for joules per gram degree C. And then the mass of the water is 120 grams. And then the change in temperature, same final temperature, minus the initial temperature, which was 21.6. Okay. That's the hard part, setting it up. The rest is just be sure you don't make any mistakes calculating. So we calculate a value for this one, calculate a value for that one, and then we solve for this one right here. And it should come out to 0.45. I'm just saving time. 0.45 joules per gram degree C, which is iron. So if I gave you a question like this and I change the parameters, you'd be able to calculate that and determine out of that list which one is which. I hope so. I'm sorry?
Is that what you're doing?
I'm just sneaky enough to do that. I'm trying to save time on calculations now so that we'll still have time to do the lab. Introduction. 28. Okay. Uh, 295.5 grams of a solid at 30 degrees. You let it melt in water at 425 grams of water, in 425 grams of water. Water temperature decreases from 85.1 to 30. Calculate the heat of fusion of this solid. The heat of fusion is how many joules per gram does it take to go from one phase to the next, from liquid to solid or solid to liquid? And that's what heat of fusion means. So let's put the information we have now. 295.5 grams. Mass equals 295.5 grams. This is the heat of the mass of the solid. At 30 degrees. So its initial temperature equals 30 degrees. See. The mass of the water equals 425. Okay. The water temperature goes from 85.1 to 30. So the initial temperature of the water equals 85.1. And it ends up at the same temperature as the solid. You know, that's important because if they don't end up at the same temperature, then you've got another factor in there for once this thing melts into a liquid, the liquid has its own specific heat, and if it changes a further temperature, then complicates the calculation, in other words. All right, here's how you approach this. You're in a calorimeter, so everything has to equal 0. That hasn't changed. But we're going to set this one apart, the Q of fusion of that solid. And we also have to assume that when you put that solid in water, it doesn't dissolve in the water. It just extracts heat from it. And then there's the Q for the water. All right. So this is going to be our unknown, the Q of fusion, the heat of fusion, which will be joules. And then the water is going to be 4.18 joules per gram degree C. And then the mass of the water, which is 425 grams. Okay. And then the change of temperature for the water. The water's final temperature is 30. And its initial temperature was 85.1 degrees C. Okay. So now we just have to solve this one. Right? 30 and subtract 85.1 times 425 times 4.18. So this together is minus 9. Let's see, 1, 2, 3, 4. Wow. Is that right? Do that again. 4.18 times 425 and then 30 minus 85.1 times that. Yep, that's right. Move it 4 places. 97,885 joules plus Q. Okay, so that's equal to 0. That means if we move this to the other side, it'll be a positive value, right? So this is the value of Q of fusion. So Q of fusion, that's just the heat of fusion for that mass. What we want to know is, that's the extensive property. We want to know the intensive property for this material, right? How much heat per gram? Right. So if this is the Q of fusion at 97,885 joules, then the heat of fusion, I'm going to call it this. delta H of fusion, because they're usually ratio is 97,885 joules per 295.5 grams. And yes, our answers are in joules per gram. So that keeps us on track. 295.5 divided is 331 joules per gram, which would be C. Okay. Okay. 28. And 32. Let's start again. Crap out on me too. In the lab, you mix two solutions, each originally at the same temperature, and the temperature of the resulting solution decreases, which is the following is true. So in the lab, we add two solutions. I'm going to say they're aqueous. And they make a product, say, whatever it is. All right. They're both the same temperature. So the initial temperature here is equal to initial temperature here. And the resulting temperature is decreased. So the final temperature is less than the initial temperature, which means what? The reaction is endothermic. This reaction absorbs energy because the temperature decreases. Okay, so what can we say? The chemical reaction is absorbing energy, C? Yeah. A, releasing energy? No. The energy released is equal to Sm delta T. You know, maybe it is and maybe it isn't. That's not the best answer. Let's see, would that be accurate though? Change in temperature, mass. You'd have to know the specific heats. I wouldn't bet on B. No, I think C is a better answer. And next one, 36. We haven't even got to Hess's law yet. Let me get another marker. That one started a bit weak. Uh, 123.7 joules will raise the temperature of 10 grams of a metal from 25 to 60 degrees. What's the specific heat of the capacity of the metal? This one is easy. I should have put this one early because Q is equal to Sm delta T. So Q in this case is 123.7 joules. Heat capacity there. And mass is 10 grams. And change in temperature. Final minus initial. Final is 60. Minus initial 25. Okay. So let's see, what is this one? For 35. Right here. 8 times 10 is 350. Correct? Yeah. So S is going to be 123.7 divided by 350. I get 0.353. 0.353 joules per gram degree C. B. B is your answer. Six 38. On a cold winter's day, a steel metal fence post feels colder than a wooden fence post of identical size because this calls for a picture. So this is our steel post. This is our wood post. Okay. And it's a cold day. And when you touch the steel, it feels colder than the wood does. Okay. So this one has a particular specific heat for steel. This one has a specific heat for wood. Right? This one would be equal to, let's see, we do Q equals S and delta T. And we solve for this one. Actually, let's not solve for just that one. Just occurred to me. What's constant in this whole thing? Well, we have to assume that the mass is the same. Otherwise, it's kind of a wasted effort. So the mass is going to be the same, and we're going to combine Q divided by mass. So it's S times delta T. All right. Now, if this is a constant, then this is a product of two variables, which means they're inversely proportional. So as the temperature change goes up, the specific heat goes down. All right. So let's go back to the physiology. If it feels colder, the temperature change against your hand is due to a more decrease in temperature. That's how your skin senses temperature. It's a change. Right? So a greater change in temperature means a smaller S value. So that means this one's got to be smaller than it is for the wood. Is there one that matches that?
Yeah, you could just read that question. I mean, if it's colder, then that would mean it's lower heat density.
Yeah. That's B. I was trying to be scientific.
Yeah, I know. I was like, why is he doing that?
Instead of just blurting it out. I'm trying to draw everything back to what we understand about heat capacity. All right, 43. Oh, we're burning alcohol again. Okay. Okay, let's see. When a 21.1 gram sample of ethanol is burned, how much energy is released? Okay, we're gonna have to put the formula, the whole equation up here for this one. C2H5OH liquid plus oxygen gas yields carbon dioxide plus water and delta H equals something. Let's see, this is a 3, this is a 2, and this is a 3. And we have minus 137 10 to the third. kilojoules. All right. When you see a delta H assigned to an equation like this, you note the sign, but also it's not going to say kilojoules per mole. If it's assigned to this balanced equation, it can be written as that many kilojoules per mole of ethanol. Or it can be that many kilojoules per 3 moles of oxygen, or per 2 moles of carbon dioxide, or per 3 moles of water. So you can put the denominator in here based upon these mole ratios, whatever the problem you're going to solve. The problem here says 21.1 grams of ethanol, and we want to know what the energy there. So this is in terms of 1 mole of ethanol. But we don't have it in moles. We got 21.1 grams. So that has to be changed to moles, right? Grams per mole. Does it tell us? 46.07. 46.07 grams per mole. So that's going to be a little less than 0.5. It's 0.4 something. Four, 5, 8. 0.458 moles. Now we can multiply this times that value, minus 1.37 times 10 to the third kilojoules per 1 mole of ethanol. Moles cancel, leaves us with kilojoules. Answers in kilojoules, good. Okay, so I'll multiply this value I have here times that value. 1.37 exponent 3. And I get, let's see, it's got a mixture. Let's see, scientific notation would be 6.27 times 10 squared. Kilojoules. Is that one in there? Yeah, C. So the answer is C.
I'm sorry, my head's not right. I just had to quit my bill.
Really?
Yeah,
Oh,
yeah. But I love it, really, I do love it a lot. I'm very proud.
were you forced to?
Kind of, they told me that every day that I didn't have school, I would have to work. That means I would be working every single Wednesday, Thursday, Saturday, Sunday, every single week.
Oh,
And I have to, yesterday I did this homework all day. Like I have to have a day to do homework. I can't.
yeah.
And it's not my career job. It's
Okay.
hard to be brief, but yeah.
Yeah.
My head's on me. Sorry.
I understand. So you got to find some income. Great.
I'm getting paid by school. That's the thing. I don't really need this money. I was just working for like extra money.
Oh, okay.
But, I get paid a ridiculous amount of money to like play bingo and play games with old people. Like I'm an activities director at the nursing home.
Oh, okay.
Yeah, so I get paid really good to do not very much. So it's
Yeah.
a really good job for me.
Yeah, my wife was activities
And I
director
love it so
when she
much.
was ambulatory.
Yeah.
She's retired
I
now.
just enjoy it. So
Yeah,
I'm
she
happy
did.
about it.
I understand.
Just- Kind of crazy.
My wife had training to work with Alzheimer's patients.
That's what I do.
Yeah.
I love it. I love it. I'll go volunteer there. or something.
Bummer. Now I just feel like quitting, but I'm not. Total volume of hydrogen gas you needed to fill the Hindenburg was 2.11 times 10 to the 8 liters at 1 atmosphere, 24.7 degrees Celsius. How much energy was evolved when it burned? Right. Has everybody seen like the movies of the Hindenburg crashing and burning? You haven't? Oh, you ought to. Yeah. You got people you see people falling out of it, and you see people running from the flames. It was a disaster for sure. What's amazing is that there weren't as many people killed as were actually on the thing when it went down. A lot of people got out. Okay, so we've got this equation. Hydrogen gas is combined with oxygen gas to yield water. And is that a gas? No, it's a liquid. It's a liquid. Okay, and the delta H for that is minus 286. 286 kilojoules. Okay. First thing you'll notice about this equation is it's got a fraction in it for coefficient. That's probably because this is the heat of formation for water. Remember how you do heat of formation? You start with the product, 1 mole of the product in its most stable form at room temperature and pressure, and work backwards. So you need hydrogen in its most stable form and oxygen in its most stable form. And then you use fractionals if you need them to give you exactly how many of these you want. Okay, so now we've got 2.11 times 10 to the 8th liters. And pressure is 1 atmosphere. All right. Temperature is 24.7. 24.76. All right. How are we going to get a handle on this? Right. This is in terms of moles. Right. This many kilojoules evolved for 1 mole of hydrogen. Right. And these are the particulars about that hydrogen. So how are we going to get at the number of moles? How about ideal gas equation? Solve for N. So that's PV over RT. Pressure is good, right? If R is in liter atmospheres per mole K, then atmospheres is good. 1 atmosphere. Volume, it's in liters already. That's good. Okay. How about R? Well, R is a constant. And temperature. Well, temperature is in C, so we got to add 273 to it. So that'll be 0.7. And then 3 and 4 is 7. And 2 and 2 is 4. No, excuse me. Let's try that again. 4 and 3. 4 and 3 is 7, yeah. And 2 and 7 is, no. 4 and 3 is 7. 2 and 7 is 9. Here we go. That's what I get for trying to do it in my head. Divided by 0.08206 and 297.75. So the number of moles is equal to 8.64 times 10 to the 6th moles. So now we just need, what's the heat relationship here? Per mole of hydrogen is minus 286 kilojoules. And I get 2.47 times 10 to the 9th kilojoules. Well, I put the negative here because that means it's exothermic. But the problem says how much energy was evolved. That automatically means exothermic. So D is the answer.
I'm
Okay.
Like this for,
Sorry.
so can't we go to sleep? I've been up for. But because it's 9 o'clock yesterday, I haven't bed since 9 o'clock yesterday.
That would kill me.
And I worked last night. Okay.
Yeah. I got to bed 11, got up at 4, so that's something.
That's bad too. Honestly.
Okay, 46. Did we already do that one? No, we didn't do that. 46. Methane plus chlorine gas yields carbon tetrachloride plus hydrogen chloride. And it's an exothermic reaction with minus 434 kilojoules. What energy change occurs when 1.2 moles of methane reacts? So we don't even have to write this up, the formula up there. We know that delta H equals minus 434 kilojoules. And that's for that equation. And ratio to methane is per 1 mole of methane. Because there's only, the coefficient is 1. So 1.2 moles of methane right, cancels moles. And 434 times 1.2. Oh, they've got it in joules. So I better work this one out. 434 and 1.2 is 521. Oh, this is 1.2, so I got to round it off. 520, right? 520 kilojoules. Our answer is in joules. All right. So you remember the way to handle this one. Kilo means 10 to the third, right? 520 times that. Okay. So this one's going to be 5.2 times 10 squared times 10 to the third joules, or 5.2 times 10 to the fifth. And that's, oh, absorbed or released. It's negative, right? So it's released. Yeah. You have two choices there. So it has to be negative. It's exothermic. Okay. 51. Consider the following specific heats of metals. If the same amount of heat is added to 25 grams of each of the metals, which are all at the same initial temperature, which metal will have the highest temperature? All right, so if we go back to here, and it said the same amount of heat, so that one's constant for each of the metals. This one, of course, is different for each metal. And the masses are the same, 25 grams, right? And then the delta T is T final minus T initial. This one's constant. This one's constant. So this delta T is going to change with respect to that one. And this is constant. Yeah, those are all constants. So this is like that problem before. If this is constant, these are constant, then if this one goes up, that one has to go down. But we're looking for the largest final temperature, the highest. If this one goes up, that one goes down. So the smallest value for S is the one with the largest temperature change, which would be lead. All right. I'm going to skip all these A's and B's and D's. I don't like those. I use them sometimes, but I don't like them. All right, this one's going to take some work. We're getting into Hess's law now. So let's see if I got enough board room to do it. All right, given these different reactions, component reactions, and their enthalpies, we want to determine the enthalpy for this target reaction, P4O10 solid. P4O10 solid plus 6PCl5, is it? Gas yields I better start over further to the left. See, I need to put the number up here, 59. P4O10 solid plus 6PCl5 yields 10. Oops. Yeah. Cl3PO gas. And the question is, what is this? All right, the way I work Hess's law, I take the target equation and I look for, in the given equation, I look for each of these components. And I just go down the line. Right? So in Roman numeral 1, do we find any of those? No, there's a PCl3, but not a PCl5. So we skip Roman numeral 1. We can't use it yet. We will, but not yet. So number 2 gives us P4O10. Right? All right. But notice that P4O10 is on the wrong side. Correct? Okay. So what happens when you have to flip the equation? The delta H changes sign. It's exothermic this way, it's endothermic that way. So when we rotate it over and put P4O10 on this side where it needs to be, we change the sign of our delta H. And that's all we're going to have to do because we only need one of them, and there's one of them in that equation. So I'm going to do that one right now. So we got this P4O10 solid, and we're going backwards. So I'm going backwards to P4 solid plus O2, meaning 5. And now the delta H is going to be positive 2967.3. 2967.3. These are all kilojoules, aren't they? Yep, kilojoules. Positive. Okay, we're going to use this one. So I always put an asterisk there because when we have all these lined up, if we do changes, I don't want to use one that's not supposed to be. So I mark this one as the one that we're going to use to add together in Hess's law to make that one. How about the next one? 3. PCl5. It's got a PCl5 in it, doesn't it? PCl5 is on the wrong side. It needs to be over here. Plus, it needs to be multiplied by 6. Okay, so if we flip it over and get 6 PCl5, let's see, I didn't put that's a gas. And PCl3 gas. Okay, I've multiplied it by 6. Right, so this has to be 6 also. And this one has to be 6. Cl2 gas, correct? Okay, now we did flip it. So this is now plus 84.2 times 6. So that's 505.2 plus 505.2 kilojoules. Okay, so we're going to use this one. We're going to use this one. Okay, so that takes care of that one and this one. We need Cl3PO. Cl3, the last one. Okay. It's good. It's on the right.
But multiply the kilojoules by 10.
Yep. Multiply by 10. Mhm. So we got, we need 10 of these. Cl3PO gas. And then PCl3, 10 times PCl3, right? Gas. And then oxygen is a half times 10 to be 5. Right? 5 oxygen. And then we multiply. We didn't have to flip it, so it's minus 285.7 times 10. Or minus 2857 kilojoules. That, and that takes care of this one. Now, we've got this one that we kept for that one. We've got this one we kept for that part. And we got this one that we kept for that part. We got to get rid of that one, that one, that one, that one, this one, and that one. We don't need those. So can we get rid of any of them now? Before oxygen. 5 oxygen on that side, 5 oxygen on this side. It's gone. Let's go back to Roman numeral 1. Okay. Roman numeral 1 has P4 on the left. P4 is on the right here. So I think we're good just to leave it like it is. So we have P4. What else? 6 Cl2 plus 6 Cl2 gas yields 4 PCl3. 4 PCl3 gas. And that value is 1225.6 minus 1225.6 kilojoules. Okay. Now let's see if I cancel correctly. P4, yeah, P4 cancels. See on this side, 6 Cl2, yep, that cancels. How about 10 PCl3, 6 here and 4 there? So those cancel. Those 10 cancel by this one. And that leaves us with that one. This one, this one. We're good. Now, if you add them together, you get that equation. And we got this, 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 and this to combine. So 2967.3, 505.2 added. Is that right? That's still minus, isn't it? Okay. 2857 minus and 1225.6 minus. So I get delta H equals minus 6 N kilojoules. 0.1. Do I have a 0.1 here? Yeah, I do have a 0.1. Cross all my T's and dot my I's. That took some work. There's no doubt about it.
whole time I've been writing kilograms about density.
Naughty.
That work equation, it really like throws you for a loop because in physics, you learn that word is force.
Times distance. Mhm.
That's hard.
And it still is.
Yeah, but on. What was it?
And that's where we started in the lecture. We started work equals force times distance. And it's negative pressure times change in volume. Yeah. And we used an expanding gas to make the transition from force times distance to pressure times volume. All right. What are we doing on time? We got an hour and 15 minutes. We might run out of time for the lab. I do have a video introduction for this lab that, yeah, Waters of Constitution and Hydration that I did for my class in Beckley. So if we run out of time, I'll post that.
Material.
It actually works out the pre-lab question. And that shows you how to determine waters of hydration, where you have the salt and a dot and then so many waters. It goes through that one in detail. And then I've got a document. I haven't checked to see if it's in your Brightspace, but I've got a document that explains what you do with the numbers when you get them after the lab. So I'll be sure that's posted also. All right. 68. Choose the correct equation for the standard enthalpy of formation for carbon monoxide gas, where delta H, standard delta H formation for CO is minus 110.5 kilojoules per mole. GR indicates graphite. Graphite is the most stable form of carbon. So we're going to start with the product. That's where you always start with the heat of formation. Then we work backwards. So we're going to have graphite here and oxygen gas here. Right? We've got one C already. That's good. We need only one oxygen. So we need a half there. And the delta H of formation is given to us. Minus 110.5, was it? Kilojoules. So which one matches that? C. Okay. That's how you do heats. That's how you do formation equations. You start with the product, work your way back. Let's see. I skipped a few. There's a lot of repetition in here. 78. One of the main advantages of hydrogen as a fuel. All right. So what do you get? If you're going to use hydrogen as a fuel, what do you combine it with? No, combine it with oxygen. And it produces water. Hydrogen gas plus oxygen gas yields water. All right, so we need two of these to make oxygen and 4 of these. So that's not the heat of formation, but it doesn't matter for our purposes here. So one thing that's great about this is that the only product it produces is water. And out of those 5 possibilities, that's the best answer. It exists as a free gas. Well, not really, not in significant amounts to be used as a fuel. We have to make it. In fact, hydrogen now is made from methane, which is bad because it produces carbon waste. Well, it's bad according to some people. So that doesn't help any. It can be economically supplied by the world's oceans. Well, maybe it could if we could get everybody on board for nuclear power. Because the oceans are like all that water, and all you have to do is just reverse this reaction, right? Use electricity. Let's see what we do. Electromotive potential. Just zap it with direct current, and you can make hydrogen and oxygen out of it. But the key is, where do you get that electricity? Right? If you don't get it from renewable sources like solar or wind, which are unreliable and not nearly enough, your only other option is nuclear. So if I haven't said it before, if a greenie gets in your face about carbon pollution and all that other crap, and you ask them this question, where do you stand on nuclear power? If they're against nuclear power, then you can turn and walk away because they're just completely wacko. Plants can economically produce hydrogen. No. Plants do one thing. They take carbon dioxide from the air, they combine it with water using, well, most of them, the green plants, they use H-nu. Remember that one? Energy. Okay. They use energy from the sun to break bonds and reconnect them, and they make carbohydrates. Plus, their waste product is oxygen gas. So that's why we can live, because they make oxygen for us, using carbon dioxide as a fuel, as food. Okay, so that doesn't work. It contains a large amount of energy per unit volume of hydrogen gas. Well, actually, it doesn't. It's very energy diffuse. That's one of the big problems, right? How do you get enough hydrogen, say, in your vehicle, if you're going to use it as a fuel, to either run it in your combustion engine or use it in a fuel cell, right, to make electricity directly? You got to have a way to store a lot of gas in a small space, and that means, well, one of several things. One possibility is pressurized cylinders. Right? You don't want one of those around when you have a car wreck, because those things blow up, you in big trouble. So they're looking at other possibilities where you have hydrogen is fed into a container that's got a material in it that absorbs the hydrogen just strongly enough to keep it there, and then it releases it on demand. Right? But that last one is not true. Hydrogen is good for making only water. Right? A is the only answer that works. I could have said that out right up front, but I wanted to talk some more. Okay, that was 78. 79. All right, which of the following is not being considered as an energy source for the future? All right, ethanol, right? We make ethanol from corn now, and we put up to 10% in our gasoline. It's on every gas pump in the country. Of course, there are disadvantages to that, right? You have to have special, if you go over 10%, you have to have special tubing in your engine. Otherwise, more ethanol than that will damage the tubing. It also is hard on the engine. Methanol is just as bad or even worse. Seed oil. Seed oil could be a useful energy source for diesel engines. When the diesel engine was first invented by what was his name? Rudolph Diesel, I think his name was. I thought he was German, but he's actually French. And the fuel that he used in his engine was vegetable oil. So he built his first engine for vegetable oil. And we transitioned later to a petroleum distillate, diesel fuel. So I saw this program one time. These people wanted to drive across the country. They wanted to use a bus with a diesel engine, and they didn't want to pay for the fuel. So they'd stop in every major city, and they'd go to restaurants. And they'd have this waste oil from their fryers. And they take that stuff and just dump it in their tank and go on their way. Well, it goes through a filter. And you do have to preheat it. Now, if you don't preheat it before it goes into the carburetor, then it'll gum things up. But other than that, it ran fine. They're not exactly the same, but they have similar energy outputs. Yeah. Right, seed oil. Anybody, you had anatomy and physiology?
Yeah.
Okay, so they told you what a true fat is. That's what the kind of oil we're talking about. So it's a triglyceride. Shale oil. Right? Shale oil's good fuel. Right? You can go in now to formerly exhausted oil fields and go down with another drill head and horizontally drill into the formation and then poke holes in your pipe and then push this special formula of water and mud and other stuff down there in ultra high pressure, and it cracks the formation and more oil can be drawn out of it. That's called fracking. They do that for gas too. So shale oil is difficult to get at without fracking because the shale is so dense. It doesn't let the oil move. Carbon dioxide. If you stick around for next semester, we'll find out that carbon dioxide cannot be a fuel. Yeah, I mean it's a waste product. Mm-hmm. When you burn any of those others, you get carbon dioxide. So it has to do with its oxidation state. Yeah. We breathe out carbon dioxide. Right? When we take sucrose in or carbohydrates in or proteins or fats or anything, they end up eventually producing carbon dioxide and water. And then of course, if they have nitrogen in them, that's another product. But you got to get rid of the carbon dioxide, so you exhale it, and the water just sticks around, right? And if you have too much water, then your kidneys get rid of it. Okay, so the answer to that one is E. Carbon dioxide cannot be a fuel. All right, we're going to skip those. Go down to 90. Oops. Zero out. A gas absorbs 188 joules of heat and then performs 310 joules of work. The change in internal energy is. All right, we'll go back to internal energy is Q plus W. So if a gas absorbs 188 joules of heat, let's draw a picture. And so we got a piston. So absorbing 188 joules is a positive value, right? Because it's going into the system. But the work that it does, 310 joules of work, as it moves this direction, it's doing work on the surroundings. It's losing, this is Q, it's losing 310 joules. So now that we know what our signs are, we can put them together, right? And as it turns out, the change in internal energy is negative. This system is losing internal energy to the tune of minus 122 joules. Okay, just add those two together. This one's bigger than that one and it's negative, so the value is going to be negative. Minus 122 joules is the change in delta.
When we take this on one, how do we write that delta?
That's a question for you. I'm sure there's a way.
You shouldn't have to, right?
I mean, you don't require us to work it out. I just thought that you wanted us to work it.
Oh, the extra credits, yeah. The extra credits, right. Let me take a look at it and see the structure of the exam. Let's see, this is yeah, this is right.
If we do have to, I can just submit a picture of doing it on.
Yeah,
I don't care. I mean, that's not hard. That's no big deal. But
yeah, for the bonuses, you do have to show your work.
Yeah.
So do it on a separate piece of paper and photograph it. And you can, when you submit your or upload the document,
Yeah.
you're able to upload more than one file
Yeah.
at a time. So you can
We'll
just
upload that.
tack those onto it. Okay, that was 90. And let's see, 99. Let's see, can I fit that in there? Yep. 99. Nitric acid, HNO3, is first prepared 1,200 years ago by heating naturally occurring sodium nitrate, saltpeter, with sulfuric acid to produce sodium bisulfate and collecting the vapors of HNO3 produced. Right, so how do they collect those vapors? Does the apprentice sucks them into his lungs and blows them out somewhere else? No.
Mhm.
They probably bubbled it through water. HNO3 will dissolve in water and you got nitric acid. Okay, so we've got this, this is the controlling equation. Plus, that's saltpeter plus sulfuric acid yields sodium bisulfate. The bi refers to a hydrogen. It's like sodium bicarbonate. Baking soda is sodium hydrogen carbonate. This is sodium bisulfate. Right? Like it's a holdover from ancient times. It should be, the proper name now is sodium hydrogen sulfate. And then nitric acid. Now this is balanced equation. You can see one sodium, one nitrate, two hydrogens, one here, and one sulfate. So that's balanced. What they want to know is what's the delta H for that reaction? And they're giving you the heats of formation. So the heats of formation for compounds are real values. The heats of formation for elements is 0. So if you have an equation with elements in it, then you just put in a 0 for those. And the formula, the delta H for this reaction is the summation of the products, the heats of formation for the products. See there, formation for the products minus the sum of the heats of formation for the reactants. Now put that N in there. That N is coefficients. If you have a coefficient there, each one of the, does everybody know how to do a sum? Right, you know what the sigma means? Okay. So you do each one, like you have a value for this one times its value, then you add together this one times its coefficient, and you subtract these from these. But they're all one, so that makes it a lot easier. Okay, so how about the products? Well, the products are sodium nitrate, which is minus 467.8. Minus 467.8 kilojoules. And then we add sulfuric acid, minus 814. kilojoules. Right? And then we subtract whatever we get in this one. Wait a minute. I did that wrong, didn't I? I sure did. Nobody caught me. Products first. Okay. Sodium bisulfate minus 1125.5. Minus 1125.5. And then nitric acid, which is minus 135.1. Now I can go back to sodium nitrate, minus 467.8. These are all kilojoules. And what did I say? Sulfuric acid next, minus 814. There we go. So don't forget that this is a negative, that's a negative. They're all negatives. But this negative makes this term positive. Okay. And if you work it out correctly, you should come out with 644.2. 644. No, 21.2, excuse me. Delta H0 equals 21.2 kilojoules. So it's an endothermic process. You have to add heat to it to make it go. And the method says by heating naturally occurring sodium nitrate with sulfuric acid. I think that's the last one. Okay.